The USS John F. Kennedy, CVN-79, the United States Navy's second Ford-class aircraft carrier, has reached a critical milestone in its long and complex development with the completion of its first nuclear propulsion tests. Conducted in the James River at Newport News Shipbuilding, the tests involved maneuvering the 100,000-ton vessel with tugboats before returning it to the pier for further trials. This event represents not just a technical achievement but also a moment of strategic importance, signaling the Navy's continued investment in next-generation carrier capabilities despite the program's persistent delays and logistical challenges. The Kennedy's propulsion testing is a tangible demonstration of progress in a program that has spanned more than a decade, combining advanced engineering with lessons learned from its predecessor, the USS Gerald R. Ford, CVN-78. Construction of the Kennedy began shortly after contract awards in 2009, with the keel laid in 2015 and the installation of major components, such as the 588-ton island and forward catapults, occurring in 2019. The ship's assembly has followed a rigorous sequence of structural milestones, carefully orchestrated to accommodate the integration of cutting-edge systems. Among the most transformative of these are the Electromagnetic Aircraft Launch System, EMALS, and the Advanced Arresting Gear, AAG. EMALS, first trialed in 2022, replaces traditional steam catapults with an electromagnetic system capable of launching aircraft more efficiently and with less stress on airframes. The AAG, on the other hand, introduces an electromagnetic arresting mechanism that allows the carrier to recover a wider variety of aircraft, including lighter unmanned aerial vehicles, while reducing the wear on both the landing gear and the airframe. Despite the promise of these innovations, certification difficulties and technical challenges have contributed significantly to the delays in the Kennedy's commissioning. In addition to launch and recovery systems, the Advanced Weapons Elevators, AWE, have emerged as another critical element impacting the carrier's schedule. Designed to transfer ordnance from magazines to the flight deck using electromagnetic linear motors, the AWEs aim to improve efficiency and reduce handling times compared to older hydraulic elevators. However, as observed with the Gerald R. Ford, installation and reliability issues have required iterative adjustments, prolonging the final certification process. These technological complexities, combined with workforce shortages and supply chain disruptions at the shipyard, have pushed the projected delivery date to March 2027, nearly 2 years later than initially planned. This delay carries strategic implications, leaving the Navy temporarily without a full complement of carriers following the retirement of USS Nimitz in 2026. The Kennedy's radar and sensor suite exemplifies the evolution of carrier-based detection and targeting capabilities. Departing from the dual-band radar configuration of the Gerald R. Ford, CVN-79 incorporates a combination of the N/Spy 3X-band multifunction radar with the new N/Spy 6V3 Enterprise Air Surveillance Radar. The SPY-6V3 utilizes gallium nitride semiconductors and digital beamforming technology, delivering enhanced sensitivity and reliability while reducing maintenance requirements. Its three-faced fixed-array design provides complete 360-degree coverage and performance capabilities estimated at up to 35 times the sensitivity of legacy SPY 1D systems. This integration of modern radar technology not only enhances volume search and target tracking but also aligns the carrier with the radar suite used on Flight 3 Arleigh Burke-class destroyers, promoting interoperability and cost efficiency across the fleet. The physical specifications of the Kennedy underscore its role as a transformative platform in naval aviation. Stretching 337 meters in length with a flight deck width of 78 meters and a waterline beam of 41 meters, the carrier is designed to operate more than 80 aircraft under normal conditions, with surge capacity for up to 90. This includes a mix of F divided by a -18E divided by F Super Hornets, EA-18G Growlers, E-2 Hawkeyes, C-2 or CMV-22 aircraft, F F-35C Lightning II fighters, MH-60 helicopters, and unmanned aerial systems. Nuclear propulsion is provided by two Bechtel A-1B reactors, each surpassing the output of the Nimitz-class A-4W reactors. These reactors generate sufficient electrical power to drive 4 shafts and supply energy to the carrier's advanced systems, enabling speeds exceeding 30 knots and operating endurance of 20 to 25 years before refueling. The combination of reduced crew requirements, around 4,660 personnel, and enhanced automation reflects a shift in carrier design philosophy, emphasizing operational efficiency without compromising capability. Programmatically, the Kennedy represents a significant investment in the Navy's long-term maritime strategy. Funding for the carrier has included a $3.35 billion fixed-price incentive award and a $941 million cost-plus modification for final design, construction, and life cycle support. These contracts cover not only the construction of the hull and flight deck but also research and development, fabrication of unit assemblies, and preparation of detailed support documentation. While the ship was launched in October 2019 and christened shortly thereafter, delays in integrating advanced systems have necessitated a re-evaluation of delivery timelines. The Navy has even considered accepting the carrier with certain non-essential work, such as painting, unfinished in order to mitigate the operational gap created by Nimitz's retirement. Such measures underscore the strategic imperative of maintaining carrier presence while acknowledging the complexities of modern shipbuilding. The implications of these delays extend beyond the ship itself to the infrastructure required to support a Ford-class carrier. Plans to homeport the Kennedy at Naval Base Kitsap Bremerton, projected no earlier than 2029, involve extensive electrical distribution upgrades, including the replacement of an existing substation, construction of a new pier substation, and modernization of transformers and switchgear. These enhancements are necessary to accommodate the significantly higher electrical demands of advanced systems such as EMALS, AAG, AWEs, and the SPY-6 radar compared to legacy Nimitz-class carriers. The relocation will also bring thousands of personnel and dependents to the region, further highlighting the logistical and operational considerations of introducing a next-generation carrier into the fleet. From a strategic perspective, the Kennedy's integration into the U.S. Navy marks a continuation of the transition toward carriers that are not only larger and more capable but also more versatile and technologically sophisticated. The combination of electromagnetic launch and recovery systems, advanced weapons handling, and next-generation sensors positions the Kennedy as a platform capable of supporting fifth-generation aircraft and unmanned systems from the outset. This approach contrasts with previous carriers, which often received incremental upgrades over their operational lifespans, reflecting a deliberate effort to reduce retrofitting costs and improve operational readiness from day one. Moreover, the lessons learned from Gerald R. Ford's construction and testing have informed the Kennedy's design, providing opportunities to address known issues proactively, even if challenges remain in certifying critical subsystems. The broader programmatic context also emphasizes the Navy's focus on sustaining a continuous carrier presence while modernizing the fleet. CVN 79 is the second of 10 planned Ford-class carriers, with the Enterprise, CVN 80, and Doris Miller, CVN 81, already under construction. The Kennedy is set to replace the Nimitz, which will retire after more than 5 decades of service, ensuring that the United States maintains its global power projection capabilities. By incorporating state-of-the-art technologies, streamlining operations, and reducing crew requirements, the Ford-class carriers are positioned to remain relevant against evolving threats through the mid-21st century. Ultimately, the first propulsion tests of the USS John F. Kennedy represent both a technical and symbolic milestone. While delays have extended the timeline for delivery, the successful operation of the nuclear reactors and the ship's maneuvering capabilities demonstrate that the vessel is steadily approaching operational readiness. The Kennedy embodies the convergence of advanced naval engineering, strategic foresight, and lessons learned from previous construction programs, highlighting the challenges and rewards of producing a modern aircraft carrier capable of supporting the full spectrum of naval operations. As the Navy navigates the transition from Nimitz-class to Ford-class carriers, the Kennedy's progress provides insight into the future of carrier aviation, fleet modernization, and the evolving role of the United States in global maritime security. With its advanced propulsion, radar, and combat systems, the USS John F. Kennedy is set to redefine carrier operations for decades to come. Despite setbacks in construction and certification, the vessel reflects the Navy's commitment to technological superiority and strategic flexibility, ensuring that the United States retains its edge in naval power projection well into the 2050s. The completion of propulsion testing signals a tangible step forward, providing a glimpse of the operational capabilities that will define the next generation of aircraft carriers. As the Kennedy moves closer to active service, its journey illustrates both the complexities of modern warship construction and the enduring significance of aircraft carriers in projecting power across the world's oceans.